Okay, so we are going to switch gears a little bit, and I think I'm going to give you more of an overview of the difference and the similarities between spin and orbital angular momentum, or momenta. Okay, so let's start with classical examples, because that's where these concepts actually come from. So classically, orbital angular momentum comes from orbits, right? Motion of some body or an object, about some, fixed axis outside itself. So, for example, can somebody give me an example?
The planet's rotation
Right.
around the
That's
sun.
where the orbit comes from. So here we have the sun, which is traditionally written yellow, and around it, we have, say, the pale blue dot, and it's orbiting, and we have some angular momentum associated with it. So this is orbital angular momentum. But on the other hand, if you look at the Earth and look at its spin around its North Pole, South Pole axis, is that the right way it's spinning? If this is north? No, it's the other way, right? Yeah. So it should be the other way around. So there's an angular momentum associated with that spinning, and that is called the spin angular momentum. So spin angular momentum is the angular momentum that is associated with the rotation of the body, around some axis that goes through the body itself. Okay. So in quantum mechanics, we generalize these ideas, and for example, from the motion, from the same motion, and I'm going to put motion within quotations because it's quantum motion, from the motion of electrons, say, around the nucleus, we get, say, the orbital angular momentum, right? This is just an example. Yeah. And we can define it by R cross P. And here what I'm doing is that by dividing it with H bar, I'm making L to be dimensionless, so that when we do the commutation relationship of L, H bar doesn't occur explicitly. Okay, this is just for convenience. Okay, so and we saw that L bar was a pseudo vector. But if I do a rotation, it should transform like a vector, right? Do you guys know how vectors transform under rotation?
I don't think I know exactly what it is.
Okay, so basically what I'm saying is that suppose you have a reference frame and you make a rotation of your system, and that rotation is represented by some,
Oh yeah, now I got it.
matrix R. And if you're, suppose that in your system you had some vector V, then under the rotation, the ith component of the vector will be replaced by a new vector, V prime of I. And V prime of I will be given by Rij, which is a matrix element acting on the old vector Vj. So there's a sum over J here. So what I'm saying is that if you make a rotation of your reference frame, then your angular momentum vector will, although they're operators, they're still vectors. They will change like this, okay? Your Li will go to new operators, L prime of I, which would be related to Li through, this equation. So, but under parity, of course, Li will not change sign, and that's why it's a pseudo vector. Okay. So what about spin in quantum mechanics? So spin in quantum mechanics, just in classical mechanics, arises from or I should say, spin in quantum mechanics is intrinsic to the body, to the system. So let me unpack this statement. What do I mean by intrinsic? So suppose we have a proton. A proton will have spin, and it actually has spin half. Its L value is actually half. But the way it comes about is that a proton is not a point-like object. A proton consists of, even smaller particles. So the spin of the proton is a combination of the spin slash or the orbital angular momentum of the objects inside. Suppose we did not know what these objects were. We know them to be quarks, but suppose we didn't know. Then it could be some combination of both these are quarks, we know now, but suppose we didn't know what they were. Suppose they were just some objects that we can call a parton. Suppose that, but these partons had spin as well as some angular momentum, orbital angular momentum due to their motion. And so the spin of the proton would emerge as a combination of all the different kinds of angular momenta of the internal constituents, okay? Just like the Earth. Earth's spin comes from everything in the Earth spinning around the axis of rotation. Now, if I look at an electron is a point-like object, as far as we can tell. So the spin, but it has spin which is not zero. It's a spin half particle. So we cannot really associate some sort of rotation with the electron because, what does it mean for a point-like object to rotate, right? So that's why, we call, that's why we say that, spin doesn't always have a classical analog. In the case of electron, it doesn't, but But for composite objects, spin does have a classical analog, and suppose that's the Earth. Okay. There are caveats to this story that we will get into, because the spin, whenever we have half-integer spins, there are some weird quantum effects that we don't see in classical world, but we'll get into that soon. Okay, but so this is I'm just trying to demystify the idea of spin. Spin is something that is maybe intrinsic to the particle, or it can emerge from the constituents. The idea is that, because we are not probing inside the proton, we are agnostic about the constituents of the proton, and therefore, we say, okay, it has some spin. Okay, any questions? I mean, this is I know it's a bit vague, but.
So far, no question.
Okay, so I mean, so far only Nahi and Srijosh is talking. I mean, other people should also sometimes say something, just to, I'm sure you guys have opinions. Okay, anyway, maybe I should, maybe from the next class I will use the back channel chat so that those people who are shy can post questions anonymously, okay?
Okay, sir.
Okay, so in the next class, we'll go more into it, but let me just say something about the total angular momentum. So the total angular momentum of some system, suppose the atom, usually consists of two parts: the orbital angular momentum and the spin angular momentum. And the orbital angular momentum and the spin angular momentum, they don't commute. Well, they commute, sorry. And then J squared is L squared S squared plus 2L dot S. Okay, so L and S act on different Hilbert spaces. Therefore, L dot S can also be written as S dot L. It doesn't matter. They're acting on different Hilbert spaces. Okay, we'll come back to these sort of things, but I just wanted to mention that the total angular momentum, consists of orbital plus the spin part.